No questions? Okay, and let me start sharing. Okay. So we have talked about matrices for the past 2 classes. So today we're going to do a problem where we are going to rotate a matrix 90 degrees. And the way it is in LeetCode is rotate an image, right? Because we were saying that matrices, or like images, are represented by matrices. So a matrix is just a grid of data, and an image is just every pixel is a piece of data in that grid, right? So an image is just going to be like, okay, this pixel's red, this one's blue, whatever. So here we're going to rotate an n by n, so a square. So n is the width. An n by n matrix, 90 degrees. Hi, Tim, just to give you the quick overview, we are doing this problem where we're going to rotate an n by n, a square matrix, 90 degrees. Okay, so again, this one is a very important question because this genuinely really does come up as an interview question. And if people give you a question on a matrix, it's very likely it will be this one. Okay, and there are several ways to solve it. So we're going to go over, I think in class today, we'll go over 2 of them. I'll talk about the 3rd one, but I didn't include it. Okay. Has anyone, I know Sam has seen this problem before. Has anyone else seen this problem before? Okay, sweet. So again, just the quick overview. How do we represent a matrix in code? Right? It's an array of arrays. Exactly. So you could have drawn this out with, where's my little annotator? Yeah, you could draw it out like this, and then here's your first array, your second array, and your third. In theory, these are the same, right? Here it's just on 1 line, here it's on 3, and you can see how it looks more like this square. Okay, so it's an array of arrays. Each inner array is 1 row, and each element in that inner array is a column value. Okay. So, oh, sorry, it's a little blurry. What we're trying to do is we're trying to rotate a matrix. This image is doing it, I took it from a site, it's doing it counterclockwise. I think we'll do it clockwise, but let's see what makes sense. You can do it either way. It's very similar. It's just going to end up, there's going to be some slight differences in how you calculate things. But in this case, they're doing it, I'll show you on the next slide how to do it clockwise. But in this case, they're taking this matrix, there's a little annotator. In this case, they're taking this matrix here and rotating it counterclockwise. So this 1 ended up here. This 7 ended up here. This 9 here, 3 here. And now same thing with the 2, right? 2 went to the 4, 4 to the 8, 8 to 6, 6 to the 2. Until we got, and then we go to the inner layer. And the inner layer is just 1, the 5 stays because it's in the center, right? Here, the 1 is going here, 13 here, 16 here, 4 here. Same thing with 5, right? 5 is going to the same place the 1 went, plus 1 more, right? So the 5 goes to here. The 14 goes to the same place the 13 went, but 1 more, right? That's important. You can see that it's going in the same place, offset by 1, right? 12 goes to the same place as the 4 went, offset by 1. And 3, same thing. And so on and so forth, until then we go to the inner layer. In the inner layer, the 6 goes to the 10, 10 to the 11, 11 to the 7, 7 to the 6. And there's no elements between them, and there's no further layers, so we stop. Okay, so when we're taking a matrix and we're rotating it, you are just taking the whole thing and moving that square. It's an n by n matrix. So this is 3 by 3, this is 4 by 4. Right? You can't do it in place, or we'll talk about it. It's different if this matrix is not square, but almost always when they give you this problem, the matrix is square. Okay. So we're taking this matrix and rotating it. So we're taking this corner, all the corners swap, and then everything next to them swaps off by 1. Right? The 4 went to the place that the 1 went, plus 1. Same thing with the 8 to the 6. And you can also think of it kind of as a square, like this square is all switching. Then here, this square is switching. Here, this square, and now. Oh, it doesn't quite work for this, does it? Okay, that's not as great. Well, it's also because they're not square themselves. Anyway, this is the idea of rotating a matrix. Any questions on kind of what we mean by rotating a matrix? And any thoughts on, any kind of patterns that we're seeing here as we do it? Anything you're noticing that we're doing over and over again, or any patterns, anything that I may have mentioned that sounds like you should take note of?
We had to rotate the inner squares or inner matrices as well as the exterior ones.
Yeah, exactly. You need to keep going and making sure you're hitting all of them. Absolutely. Anything else? Ignan, anything you have noticed or observed from this that you think might be important?
I have feeling that in the code it's different than it's visualized. I mean, I think it's gonna be implemented with the columns and rows indices. So for example, the first array has 3 elements and means like 0, 1, and 2 indexes of them. And it doesn't feel like visualizing this helps while we're gonna start coding maybe. So it feels like it's separated, how it looks on the picture and how it's gonna be implemented.
Yeah, interesting. So, you know what? It's kind of both. Like, you're right. We're going to be using the rows and columns, and it's not as simple as saying, hey, the 1 goes in this place. We'll be using the rows and columns. It is really going to help us to look at an example and say, hey, let's put in, this is 0, 0. The 0, 0 is going to 0, 2. I mean, wait, sorry, 2, 0.
Yeah.
2, 0. And this 2, 0 is going to 2, 2. Right? So, and we're going to start to see a pattern. We're now, okay, so we did that, right? The 2, I was saying it switches to the place that the 1 goes to, but goes 1 more, right? So 0, 1 is actually going to end up, oh wait, sorry, 0 going here.
1, 0.
Is going to end up exactly at 1, 0. And so on. So we're going to start to see this pattern of like, hey, the corners are switching. And now we're noticing that so first we switch the corners, but then when we look at the next element in that column or row, it's going exactly where its predecessor went, right? Plus 1 more. So each one of these is going to the same place as the one previous to it, plus 1. So here, the 2 went here. So the 8 is going to go plus 1 more. So we're going to see that we're going to calculate an offset So like how much more it needs to go than the corner element. And so we'll say, hey, you're going in the same row or the same column plus your offset. Right? So this corner element is going to go to this thing plus an offset of 0. This is going to go to this corner plus an offset of 1. And it ends up here. It's clearer here. This 1 ends up here, plus an offset of 0. This 5 goes here, plus an offset of 1, ends up here. This 9 goes to the corner, plus an offset of 2, ends up here. So basically, we're taking everything, we're moving it to the corner, and then we're calculating how much more of the offset we need to move it.
But we're gonna cut those corners in the code, I believe. So like it will not be the
So you're
point
going to calculate the
of the
offset.
coding.
You will calculate the offset in the code. You have to. You are going to, maybe what you mean by like cutting corners or, you know, doing something faster is because you're going to do the calculation in your head. You're going to say, okay, I know that this row is going to go like the row column is going to change with this. It's going to be row minus offset plus whatever. So it's going to be an O of 1 calculation where you say, hey, I know this element is going to go here. Let me move. What you're going to do is you're going to move all 4 corners. And then you move on to the next element. And you're going to move all of those corners plus this offset. And then you're going to move all of this. I guess they're not corners, but this part of the row plus the offset. And then once we're
you
back
wanna
here,
say that we are kind of trying to imagine it like they're rotating the corners of different squares. That's interesting.
Yeah. So we're looking at this and we're saying, okay, when I'm rotating it myself, this was one of the really good techniques or strategies when you're solving a problem, especially a matrix problem and linked lists, right? You're drawing out these examples and you're saying, okay, how am I doing this in my head? What are the steps? And here, if you gave me this matrix and you said, do it in place, and in place, remember, means you're not using extra space. So if you gave me pen and paper and you said, hey, take this matrix and rotate it, I would put a 1 here. I'd erase the 13. I'd remember what the 13 is, that this is a 13. I'd put the 1 here, and then I'd write the 13 here. I'd remember that there was a 16, so I'd write the 16 here. And I'd remember there was a 4, and I'd put the 4 here. So that's actually something I was going to do a little bit later, but let's do it now. Can everybody, I'm going to give you 15 seconds to get pen and paper. Oh, you can't see. There you go. Pen and paper. Give a thumbs up when you have it. Okay, Natalia's got it.
I can't find my thumbs up button, but I have it.
Okay, sweet. Okay. I want you all have it. I see Tim, Natalia, Sam, Ignat, you have pen and paper?
Yeah.
Okay. So, come on. There we go. Okay. Well, basically, I just drew a 3x3 matrix, and then you can put whatever you want. I just did A, B, C, D, E, F, G, H, A. That's it. So draw a 3x3 matrix on your piece of paper.
I should have just grabbed my Sudoku.
Yes, this is basically advanced Sudoku. There we go. Okay. So everybody's got some sort of matrix on the paper. So now in this, on the same matrix, I want you to rotate it. I'll do it too. You can rotate it clockwise or counterclockwise, up to you. Okay, has everybody done it? Anyone need more time? I'll give you 10 more seconds.
I can't do this. This is really hard.
Okay, is everyone ready? Anyone need more time?
Ready.
Okay. So this is what I had when I was crossing it out and I was rotating it in a more clear way. It looks like this. And I think you see, because of Zoom, you see the reverse, but hopefully it's somewhat clear. So basically, you can see we took here, we had A, B, C, D, E, F, G, H, I. Okay, so we had that, right? This entire row, A, B, C, went here, becomes the column, right? A, B, C becomes this part here. D, E, F became the next column over. G, H, I became this column over. Does everyone see that?
Yeah.
So we kind of, when we rotated it, we actually took these rows and kind of put them into the columns. Let's do this one more time with, make it a 4x4 matrix. Okay, let's take 30 seconds, draw a 4x4, and let's see what happens. You can draw it if you don't need to draw it on top of the same matrix if you don't want to. I was just trying to get us used to doing this in place. Because we're gonna run into some issues of making sure that we remember the variable that was there. Okay. Sam, I see what you mean when you were saying this is hard.
I
Because
can't, yeah, I don't know how to do this in paper and pencil.
you know what helped me is on the last one, I did exactly what we did on this, like in the presentation, right? Where I took it and when I was drawing it over it, I just said, okay, let me rotate the corners. A goes here, C goes down here, and I just crossed out the other one and I wrote C, and then I crossed out this and I wrote I. And then I took the one next to it. I said, okay, it goes to where A went, but +1. If you do it that way, it is easier. It helps, but at first I was also like, what? It is confusing.
I didn't make mine big enough to just like cross it out and add another number.
Yeah. Oof, okay. That was tough. I will give you that. So now that we're doing this, I am realizing the number one mistake I made during that interview. The number one mistake I made was feeling so much pressure that I didn't take the time to draw this out. I felt a lot of pressure by having somebody on the computer, etc., that I didn't take the time to draw it, and that's what I should have done. So, and at least started talking about, I didn't know where to start talking, I was panicking, etc. If you don't know what to do, draw out examples and start just saying, okay, I'm noticing this pattern or this thing is happening, etc. So if you don't know what to do, just start drawing out examples. And it can help kind of get some ideas started. Okay. How's everybody going with rotating the matrix on paper? Is anyone not done? Anyone need more time?
Did you do the letters also, this one?
I just put on the letters. You can put them whenever you want.
Let me
I
see.
put letters.
MIEA. Okay, yeah, we have the same result.
Okay.
This one?
I know that mine like mirrors it. I don't know if you can undo that, but I know Zoom mirrors your thing. So unfortunately, you're going to see my, I don't know. Are you seeing it backwards?
No,
Anyway.
I'm seeing it right.
Oh, you are? Okay, cool. Okay. So, here we go. Here's our 4x4 matrix, right? And then this is what it looks like. So we're taking A, B, C, D as before I talk about it, actually, any patterns anyone's noticed?
Well, the easiest pattern is when we turn in it clockwise.
Mm-hmm.
And in that case, like the first row, for example, becomes the last column, and the last row and becomes the first column. It's in the case of the clockwise turning, but in counterclockwise, it needs to be kind of inversed or rotated.
Counterclockwise is the same thing. It's just that instead of the A, B, C, D going here, it goes here.
Yeah.
Mm-hmm. But same, that's what I was saying. You can draw this clockwise or counterclockwise. Both are showing the same concept and principle. Yeah, super well done, Ignat. So this ABCD is here. EFGH is here. IJKL here. MNOP here. So that brings me to, I had said I wasn't going to talk about the third solution, but I'm going to talk about it because drawing it out, it's the most easily observable. So I said there were 3 ways to solve this problem. One is to use extra space. A lot of times when they ask you this problem, they say without using extra space. And if we were to use extra space, anyone have an idea what that space would look like? If I told
Like
you
the
could use
the second matrix.
Exactly. Yeah. If I said we can use extra space, then you would create a temporary matrix or like a rotated matrix, right? That it is just initialized to all zeros or something. And then you would take this original matrix here, and you would just say, okay, this row is going to go to this column, this row to this column. So you would just go through each row, and for each row,
Yeah.
you would put it in here,
Just
in each column.
populate.
So that, we might do that for homework. Okay, that's a very legitimate solution, but often they'll tell you that you can't do it because they want to see you do it in place. But here, I think I actually put down the code for that. Which is here. Here, some function rotate matrix. We create a temporary matrix. I made up, remember, if there's a function that you're like, I don't need to spend my time, this is not the main bulk of the thing, you can create a function that doesn't quite exist. So here I said, let temporary matrix get empty matrix size n, and you pass in n. Okay, so here I just got a matrix, it's initialized, it's an n by n matrix, all zeros. And now you're just going, okay, now we're going through, let row get 0 while it's less than n, the width of our matrix. Add to the rows for each column. The temporary matrix, our new one, of, this is kind of confusing, of the width, so n minus the column that we're looking at, minus 1. So this is going to be here. If we're looking at A, now we're looking here now. So in temporary matrix of this space is going to get this element. Now temporary matrix of this space, of this space, it's going to get this element, and so on and so forth. And we're going to go through each one of these row by row. And so within each row, we're saying, okay, put that into the column. Within each row, put that into the column. Okay. So this is that do it in place. And this is a really clean solution because we're saying, okay, great. For each row, we're going to do this work of going through each column field and putting it into the column, putting what we're currently looking at in our matrix into that column. So great, everyone's very happy, it's very clean, but it's using, what's the space complexity? What's the big O of space here in this case?
O(n) square.
Exactly. So I really just sneeze. Whew. Okay, I'll hold it. Whew. Okay. Exactly. Whew. Whew. Okay. Yes, it's O(n) squared. So that is not ideal. So a lot of times when they ask this question, they say, hey, do this in place. So instead of just being able to say, okay, for each row, we're just going to write over. The reason why we can't have this be in place is because it's writing over. So if we did this with a program in time, right, we'd be saying, okay, we're taking this row and we're moving it to this column. But now that we've moved it to this column, when we get to this row, now this is B instead of F. So when we move it to this column, now B is here and we've overwritten. It's a whole mess. So does that make sense, first off, why that is something, why if we start moving things and changing them in place, we lose the elements that were in the matrix. And so then as we keep rotating things, all of a sudden we're putting the wrong elements in places. Does that make sense? Because that's something we're going to come back to. So I want to make sure people understand. So if we say, okay, great, ABC is here. Let's put it in place. So we're doing exactly what I just did here, right? With this, we're taking the matrix and we're just assigning it. We're taking this column and we're taking this row and we're putting it in this column. Taking this row and we're putting it in this column. Life is good. And that's great if we have an extra, if we create another matrix, O(n) squared, we create another matrix and we take this row and put it in this column, then easy. If we're doing it in the same matrix, so we don't have a new one, and we take this row and we put it in this column, Now, when we go to take this row, well, this H has been overwritten, right? Now it has a B. So when we take this row and we put it in this column, well, now the B is here. And now that keeps happening every time we're just kind of overwriting things. So unless we do a really good job at saving certain variables and making sure that we know what originally was there, we can't use that strategy. Okay, so we're going to be doing some sort of combination. We're going to talk about how to swap things without losing them. Okay, does everybody get using extra space, how this works? Any questions on how to rotate a matrix using extra space? Anything, do you want me to go over it again, or you're feeling good? Okay.
Good.
Okay, great. Well, stop. There we go. Okay. Okay, great. So that's if we're using extra space. If we are doing it in place, then we have two other ways to solve it. One is something that I would not expect anyone to realize on their own, but it's just something that people have noticed, and this is one way to solve the problem, where people say, okay, a transpose of a matrix, is flipping a matrix over the diagonal line. So if we did that, the 1 goes here, the 2 goes here, the 4 goes here. And then flipping it over, an 8, and a 6, and a 9. Okay, so a transpose of a matrix means flipping it, mirroring it over the diagonal line. Okay, so here, this 3, 5, 7 stays the same. Whatever in the middle of that diagonal line stays the same. But then the other elements across that line switch places. Okay, so here 13, 10, 7, 4 stays the same. 3 and 8 switch. 2 and 12 switch. 6 and 11 switch. 1 and 16 switches. 5 and 15, 9 and 14. Okay, that's the transpose of a matrix. So someone said, great, I've got a matrix. I've noticed that if I take the transpose of that matrix and then I flip the columns, it's going to give me rotated 90 degrees. Okay, we're not going to go over the solution right now, but I just want you to know, because you can kind of see it here. Your rows become, oh, this is counterclockwise, I forgot. Let's do the next slide. Your rows become your columns, right? Rows become columns. So if we flip it, if we do the transpose and then we flip the columns, it will give you this. I'm not going to go over the solution right now. Feel free, please do look into that yourself. We're going to do a different solution that I think is a little bit more intuitive. But that is a total possibility. And in that case, you'd have two parts of your function. And I would encourage you, if you did that, to have paper, to have function rotate matrix, matrix. I guess you just need the matrix. I would say matrix gets transpose matrix. Matrix gets flip matrix columns. Okay, so I would, and then in the end, you're gonna, oops. Okay, this is what your function would look like. You would have rotate matrix, matrix gets transpose matrix, which is flip it over this line. Matrix gets flip matrix columns of matrix. And so then you would flip the columns. And that will give you this rotated matrix. obviously the bulk of the work is these two functions. But that's one way to do it. Okay. We are not going to do it that way. Instead, we are going to do the pattern that we talked about before, which was taking an element. So we're going to go by each row. So each row, we're going to look at a column element and we're going to put it where it's supposed to go. So we're going to put it here. And we're going to the next element in the row. And we're going to put it in the same place, plus it's offset from this. It's going to go here. This one is going to go to the same place, plus an offset of 2 now. Here. This one, same place, plus, I guess actually now we're on to the next row. This one is going to go here. This one is going to go same place plus 1, etc. So we're going to go row by row. And for each row, we're going to just focus on putting something into the place it belongs. So now I want everybody to go back to their paper. I want you to draw, let's do a 3 by 3 matrix. And instead of putting in A, B, C, D, etc., put in the coordinates. So 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 0, 2, 0, 2, 1, 2, 2. Okay, so we're drawing a matrix like this. Give a thumbs up when you're done.
Can you please show once again?
Yeah, we're just drawing a 3 by 3 matrix and you're putting the coordinates instead of the values.
Coordinates. Okay, got it. Thank you.
Mhm. Okay. I'll give you 10 more seconds.
The row starts at 0 as well. I mean,
Yeah.
the
0 column and row start at 0. Because remember, they're arrays, nothing more, right? So arrays start at 0.
whoopsie.
Okay. Anyone need more time? Okay. Now, take it and rotate the matrix. And so write down, put 0, 0 at its new coordinate. And again, if you're struggling with this, the way I really suggest doing it is do exactly what we're talking about with this algorithm. You're going to take the first one and you're going to rotate it to the corner that you know it's going to. And then you're going to take the next one and rotate that, and you're just going to go 1 by 1. So 0, 0, I know it goes here, which means 0, 1 is going to go next to it, right? And then I'm going down to the next item. Okay, so keep doing that. Okay, anyone need more time? Everyone good? Okay, now this is going to be the tricky one. Now we're going to take here And I'm just gonna put a little arrow underneath each one. And I'm gonna say what that became. So here, 0, 0 went to this corner here, which is 0, 2, right? 0, 0 became 0, 2. 0, 1 was here, and that's 1, 2, right? So this became 1, 2. 0, 2 goes here, which is the space for 2, 2. Okay, so do that as we go. Do that for each element.
What are we doing exactly? We're just are we rotating one more time or
We're not rotating one more time. We're saying where each element, so what index that got translated to when we rotated it. So the 0, 0 went to the place of 0, 2. 0, 1 went to the place of 1, 2. 0, 2 went to the place down here. This index is 2, 2,
okay, gotcha.
and so on. Mhm. And it can help if you want. You can write 0, 1, 2, 0, 1, 2. So you can see easily which ones are the rows and the columns. This is the tricky one. I can really get in your head. Okay, give a thumbs up when you're done. How's it going? I want to see a thumbs up when you're done, so I know. I can share how it made it a little easier for me. I had 0, 0, and I just looked for where it was on the other one. And then I said, okay, that corresponds to here. I have written down, this is like my key, right? Of what each coordinate is. So I found 0, 0, that corresponds to this, which is 0, 2. Or like this one here, 2, 0. So I searched for it and I found it up here. And that corresponds to here, which is 0, 0. So 2, 0 became 0, 0. If that helps, there are many ways to do it. Okay, I've seen 1 thumbs up so far. How's it going? Tell me if you, is this one, I know this one is tougher than the others, but talk to me if you're having trouble. Okay, who needs more time? Okay, somebody's got to tell me if they're ready or they're not ready. I know Natalia gave me a thumbs up, but that's the only one I saw. But I need to know how it's going for all of you. Ignat, have you finished or do you need more time?
We are rotating the coordinates right now.
Yes.
Yeah.
So basically we're just saying where they went to. So here underneath 0, 0, I drew an arrow and I said
Yeah.
that went to the place of 0, 2.
I did.
So how is it going? Have you been able to do it yet or do you need more time?
I was able to do.
You were able. Okay, great. Tim, how about you? Complicated. Yes, I hear you, Mariana. It is complicated. Okay, you know what? Let's do it. I can just do it on the screen. We can share it together. Here. Okay. Let's make it. Oh, jeez. Here. Okay. So we've got this. It'll be 0, 0, 0, 1, 0, 2. 1, 0, 1, 1, 1, 2. This is going to be 2, 0, 2, 1, 2, 2. Okay. Nice here. Okay. So 0, 0 got flipped to this. So 0, 0 became, no, that's not a good way to do it. What is a good way to do it? Okay, we'll just write it out. So here. Okay, 0, 0, when we flip it, right? We are doing 0, 0, where is it going? Right, we're taking the corners and removing them first. So 0, 0 is flipping to here, right?
Yeah.
0, 1. So let me write that. 0, 0 flips to here. So 0, 0 goes there. Became 0, 2. Okay. 0, 1. We take that, 0, 1. Where does it go?
1, 2.
Exactly, flips to here, 1, 2. Let me clear that drawing just because it's gonna mess us up. 0, 1 went here, right? So now becomes 0, 1. So it took the place of 1, 2. Okay, 0, 2. Where does that one go? Here's 0, 0. Here's 0, 1. Where does 0, 2 go?
2, 2.
Exactly. 0, 2 goes to 2, 2. Okay, awesome. Now let's keep going. So we switched these. Should we just go? Let's try. So you know how before I was saying, okay, we flip this. Now let's put this one down here, etc. Let's stick with just rows because that's how we're going to do it in the code. So we're going row by row. So this 1, 0, where does that go?
Zero, 1.
Exactly. Right? So the ones that were here flip down here. The ones that are here are flipping up here. Remember, we're taking the rows and they're going in the column. So it's going to go up here. 1, 0. Oops. Comes 0, 1. Okay. How about 1, 1? Where does that end up?
Stay.
Yeah, totally. Stays 1, 1. Okay, easy. 1, 2. So here's 1, 0. Here's 1, 1. Where does 1, 2 go?
2, 1.
Exactly. 1, 2. Okay. Third row, we've got 2, 0. Where does that one go?
0, 0.
Exactly. Oops, 0 comes 2, 0. Okay, great. 2, 1. Where does that go?
One, 0.
Exactly. Right? We're taking this, we're rotating it this way. This 2, 1 is going to go over here. Well done. 2, 1 is getting 1, 0. Last but not least, 2, 2. Hmm? What's that?
Is it, sorry, I forget. I'm always forgetting the 0, 1, 2, 0, 1, 2. 2, 2 goes, where did it go? I have it on my paper, but it's not the same as, I didn't do it right.
So here, 0, 0, and we rotated it. 0, 0, 1 here. 0, 1, 1 here. 0, 2, 1 here. Right? So that's 0, 0, 1, and 2. In this row, it's 1, 0. Wait, oh, sorry, yeah, I guess we'll do that. Okay. 1, 0, 1 here. Right? 0, 0, 1 here. Oh, sorry, 1, 0, 1 here. We're going here. 1, 1 stayed the same. 1, 2, 1 here. On this row, 2, 0, 1 here. 2, 1 went here. 2, 2, where does it go?
0, 1.
0, 2.
2.
I mean, sorry, 2, 0. Sorry, I always do that. 2, 0. It goes here, right? So this one came up here. This one goes over here. This one goes over here. Yeah? So this becomes 2, 2. And here it becomes 2, 0. Okay. So here, 0, 0. What in this row, you can see how these all changed, right? Here, something has stayed the same between all of them. What is it?
The second index.
Which represents?
Columns.
Exactly. Here, the column has stayed the same on all of them, right? So we figured out where 0, 0 goes. And then the column stayed the same. The only thing that we increased was?
By 2.
Nope, was the row, right? So here, the column stays the same. They each have column 2. So each of these, right? Each of these that are in row 0 went to column 2. Their row changed, right? The first one is row 0, then it's row 1, then row 2. Okay, how about in this row? What has stayed the same between each of these? In their final destinations, what stayed the same?
Columns.
The column. Again, the column stayed the same. And the row changed by 1. How about here?
Same thing.
Columns stayed the same, rows increased by 1. Exactly. So here we're seeing a pattern, right? That's a pretty clear pattern that we're going in each row. it's going into the column, right? We looked at that, we saw that already. How, oh, this is what I hadn't finished. Let's just. Here, each row was going into a column. Row, column, row, column. So here, it's a very clear pattern. Each element in that row goes to the same column, but the row changes. Each element in that row goes to the same column, but the row changes. Same here. Just the row is changing, but it's in the same column. Any questions on that? I want to make sure everyone really sees that pattern. This is going to help us to do it in place, to overwrite things in place.
I got it. I'm just mad that my matrix was like off when I try to write it on.
Yeah, it's tough. But what I want to really emphasize here is that in this case, with matrices, it is really important. This is one of many cases where it's really important to draw it out because it shows you the pattern, right? So what we were talking about in the beginning was like, okay, you're drawing this, but does this really help translate? And the answer is, yeah, the key to this whole thing is drawing out some examples and then you're seeing the pattern. You're saying, how would I solve this? And you're seeing the pattern here. So again, if you're ever not sure and you're stuck, etc., draw it out. And it doesn't matter if that person, if it's a virtual interview, say, I'm going to draw this out on paper. I'll try to bend the computer so you can see what I'm doing. Like put the camera down so you can see what I'm doing. Right? But don't be afraid to use that resource to draw it out. Because you couldn't, if you were in Xcode and or in VS Code, you can't draw a matrix like this, right? You need to, I mean, I guess you could, but it would be horrible. So have paper and pen next to you at every interview so that you can draw things out if you need them, whether it's a linked list, a matrix, anything. Okay. And then if anyone ever asks you a question about an image, images are represented by matrices. So this is really helpful. Okay. So now we're seeing this pattern, right? So now we're going to have to go through the matrix and one by one, move it to the correct spot. We're going to say, okay, this is row 0 and it's going to column n, right? Like it's going to the left. If there's an n by n matrix, it's going to, I guess, the space n minus 1. So there's a 3 by 3 matrix. So it's going to 3 minus 1, right? Because we're starting at 0. It's going to column 2. Okay. Does that make sense? Here, we're looking at this row and we're putting the first row, the 0th row, goes to the last column. The first row goes to the last minus 1th column. The last row goes to the 0th column. Okay. So let me write that down. I just moved this thing. There we go. 0th row goes to, so if it's an n matrix, right? It goes to the last column, which equals n minus 1. Whoops. AKA. Okay. The first row is going to go to last minus 1 column. Last row is going to go to the 0th column. Okay.
What does the n minus 1 column represent right here?
Yeah, so the last column. So here we go. This 0th row is going to the last column, right? N represents the number we were given in this problem, an n by n matrix. N is the number of rows or columns. But because we're computer scientists and we start at 0, right? This is a 3 by 3. But we count 0, 1, 2. So it's the last column is the second, is column 2. Even though there are 3 columns. Right? This is just arrays and how we count arrays. So if I give you a 3 by 3 matrix and you start counting your rows at 0, you're counting 0, 1, 2. That's why I said this is the last column, which is also conveniently, it's the n minus 1th column. So does that make sense? So here, our n is 3. Right? Our third column is the matrix is sub 0, sub 2. Right? Our last one is going to be n minus 1 just because of how we count arrays. Anyone want me to explain that more? Does that make sense to everyone? Give me a thumbs up if it makes sense. Okay, it seems like it doesn't make sense to everyone. So here we have given an n by n matrix. This is going to be 0 to 1 to whatever we keep going until n minus 1. Right? This is annotation. Here we go. This is column. Oh, no. Okay. This is column 0, column 1, column 2. Right? This is row 0, row 1, row 2. Here, this entire matrix is a 3 by 3 matrix. Right? Because when I say a 3 by 3 matrix, I'm telling you how many rows and columns, but when we actually are indexing in, as it's an array, we start at 0. So 0, 1, 2. Does that make sense?
Yeah.
Okay, great. So that's why I say the last row here, our n is equal to 3. It's a 3 by 3 matrix, n is equal to 3. Okay, so that's why our last column is n minus 1, just because n represents the number of columns, but because it's an array, we're going 0, 1, 2. It's n minus 1. This 2 is equal to n minus 1, which is equal to 3 minus 1. You get it. Okay. Which is 2. Okay, cool. All right. So, yes. Okay, great. So now we're going to be going through row by row. And in each row, we are figuring out which column it belongs to, and then just increasing the row as we go down each column, right? We're keeping the column the same, and we're increasing the row. Okay. Any questions on this? Okay, here's the columns. We're starting then at 0, and we're increasing the rows. All right. And we can X out of that. Okay. Whew, that's a lot. So we are going to go into a Replit and start trying to code this in a second. I know it's very confusing. It's really tough. But before we do that, I am going to bring up one thing that is, this is just more of what we said before. We're taking this, we're swapping the corners, and we go to the next element, and we keep swapping and etc. But one thing that is really important is remember how we were saying, hey, you can't just take this. You can't just take this and put it here and take this and put it here in place. Anyone remember why we couldn't just overwrite stuff?
Because as you keep iterating, to rotate, it's gonna overwrite itself as it goes.
Yeah. So if we took this here and we put it here, and now we took this here and we put it here, if we took this here and it's in the same matrix, it's fine if there's two different ones, right? But if we took this here, it's in the same matrix, well, this element was just overwritten here. So now we're taking this element and accidentally putting it here. Basically, we're overwriting stuff. So we need to make sure that we don't overwrite elements as we go through them. So what we have to do is we have to remember swap functions. So we've done this in previous classes, but it's been a while. So if you remember, if we have two variables, and let's just say we have var A gets 3, var B gets 2, and if we want to swap the values of two variables, you can't just say A gets B and B gets C, right? Because, where's my little thingy? Date text. Okay. If we just said A gets B, B gets A, here, oh, A gets B. So now A is 2. Fantastic. B gets A. Well, A is 2. So B gets 2. And that's not what we want, right? So what we need to do instead is we put A into a temporary variable. So here I put C, but we could say var temp gets A. Now we can say A gets B, B gets temp. Because temp holds what A originally was. Temp gets 3. Now we can overwrite A because we've saved its value. So now A gets the value of B. And B is going to get the original value of A, temp, which is 3. Okay. So this is a swap function, right? When we're swapping things, we need to have some sort of temp buffer. A temporary buffer. So some sort of variable that is going to hold the original thing so we don't overwrite it. Okay? This is very important to remember, the swap function, because it comes up all the time. So anytime you're trying to swap things, if you don't use a temporary buffer for the original one, you're going to end up overwriting it. So, oh no, that's not what I meant to do.
But and then the temporary buffer, this temporary buffer cannot be considered as extra space. When you said
For
they
space.
asked to do it in place, yeah.
Good question. Anyone have an answer to that? So if Ignat is saying, well, if you put in var C gets A, you're adding in a variable that you didn't have. So that seems like extra space. Anyone have an answer of why we're not concerned about that? But we were with creating a full matrix. What is the big O of this?
It's just reassignment, right? So it doesn't have it's of 1. Right?
So the actual assignment is O1, yeah. Creating the variable, if we created a matrix, an n by n matrix, that is O of n squared. Because for space, right? We're creating, it depends on, remember, big O is based on your data, on your input. So relative to your input, how much space or time are you adding? So if we created an n by n matrix, that means that if we have a 3 by 3 matrix, it's going to be 3 squared space because we created a whole other matrix that is 3 by 3. Now as our input goes up, we have a 5 by 5 matrix. All of a sudden it's O of n squared, O of 5 squared, because we created a 5 by 5 matrix. If we just say var temp gets matrix sub 0 or something like that, no matter how big our input is, it keeps growing. This line is always going to be constant time because we're not creating a matrix or a variable based on the size of our input. Instead, we're just creating a primary variable, which is just a variable that holds a value and not a structure, not a data structure. So it's holding a value of 3, a value of 5. So simple number assignment is O of 1. If we're doing a more complex type of data type, so if this got an array, and that array is the size of our input, that's O of n. If it's a matrix, that matrix is the size of our input, O of n squared. Okay, so it's a really good question, Ignat, and we want to do this in place. We're not creating a new data structure. We can use variables to hold things, but those are all O of 1 constant time. Does that make sense?
Mm.
Yeah, I know it's confusing, but basically when someone says in place, you can use a variable to hold a number or something like that, because that's constant time, O of 1. It depends. What you have to ask yourself when you're coming up with big O of stuff is you say, as my input changes, how is the runtime or the space time changing based on that input? So if the line you're evaluating is using your input somehow, it's going for the length of your input, etc., then that means it's increasing. It's not constant time, right? That's why a for loop is going from 0 to your array length. That means as your array is increasing, this for loop is increasing linearly. It's increasing at the same rate because you're going 0 through the number of elements. But if you just say var c gets 5, and you pass in an array of 1,000, var c gets 5 will always take the same amount of time because it's not depending on how many elements you pass in. So it's constant time. Okay.
To go over, it's constant time, but it is linear space, or because of the adding new element, or what's the space complexity for just swapping?
Sorry, I
Oh.
said time and I meant space as well. If
Okay.
you are, so here, that space, right? Var c gets, thanks, Mariana.
Yeah.
Var c gets 5. If you pass in an array or a matrix of 2,000 elements, or you pass in a matrix of 2 elements, when you hit the line var c gets 5, it's taking the same amount of time no matter what to assign 5 to a variable called c, right? You're not saying for every element in my array assign c gets 5, because that would be O of n. Instead, you're just saying c gets 5. That assignment itself isn't taking up more space based on your amount of input. So that's very similar here. When we're saying, when you do something in place, you can create a variable that takes a primary type. So like it takes a 5, a number, a string, right? Something that doesn't depend on your input. It wouldn't be in place if you're creating a whole new data structure and that number depends on your input. Does that make sense? Okay, I'm gonna run to the bathroom so quickly, but I think Natalia has a really good understanding of this. Natalia, would you mind explaining the space complexity and how it would change or not change depending on your input, and when it's constant time and when it isn't?
I just think if we use the same variable c for swapping each time, it's just one particular place in memory, and it's just one place, not. And by
Yes, you're on. Keep explaining. I'll be right back.
yeah, so I mean, if we have this temporary place and we just use it multiple times while we swap in, we put a first there, when we will put, we will put first 0, 0, element of matrix, then 0, 1 element of matrix, and so on. We just keep using the same small place, I believe, instead of creating, taking many places for amount of all elements of a matrix. That's how I understand. I'm not sure if it's correct.
Okay. I'm hearing silence, so I'm assuming, does that mean that everyone understands this, or do you have any more questions?
I feel like when we get this function in the whole code, it may be easier to understand.
Mm-hmm. Yeah, absolutely. Okay. So again, we're gonna write this in code. It's gonna be a bunch of, this is like a time that you use math, kind of. So when we're looking kind of at our matrix that we drew, where each coordinate, we see what it went to, we are gonna say, okay, now thinking about that in terms of row and column, what row and column is this going to? So maybe actually before we even go to the replet, we're gonna think, okay, if we think about this in terms of row, comma, column, how do we figure out which one it goes to? So we're gonna go through our, so here we're going through, okay, row gets 0, column gets 0. Row gets 0, column gets 1. We're going through each thing in our nested for loop, and we're reassigning it. So we're saying, okay, here we go. The row is, let's use I and J. I think it's actually gonna be more clear. So here, we are rotating through this matrix. And if we're given I and J, and here in this case, I is 0, right? That's the row that we're looking at. This row becomes, what does it become?
Stays the same.
Yeah, in this case, it stays the same. Here, though, it's, what is it here and here? What is it? What did the row
0.
become? 0. So in a for loop, that would look like I, right? Because I is starting at 0 and we're going up. So here, these are starting, here we've got I. But how do we figure out which column it goes to? Which column did this one go to?
N minus current column.
Exactly, right? So the 0th row went to the last column, which was the n minus 1. Okay? Great. So now we figure out for this row, we calculated the column, and we continue. Now on this row. The row seems to go to I again, but the column here, how do we figure out which column this one goes to? These all went to column 1. How did we figure that out?
1 minus 1
Yeah, so it's the last row, which is n minus 1, minus 1.
And
then-
n is the length.
Yeah,
Ah,
and it's the width and
Width.
height, right? So because it's square, it's going to be the width and height are the same. So it's the number of rows, number of columns. Right? This is a 3 by 3. So n is 3 here. And then in this case, here we go. Sorry, in this case, last row. This is n minus 1, which gets us here, minus 1, minus 1. Right? So here, this is n minus 1 minus 0. Gets us to this last column, right? Here, it's n minus 1, which is this column, minus 1. Because we're backing off, or one less. One column behind the last one. Here, this is n minus 1, minus 1, minus 1. Gets us here. And so on and so forth. If this was a 4 by 4, it would be this row, then this. I mean, this column, then this one, then this one. Right? So we're seeing this pattern where this row first moves into the last column, which is n minus 1. Then it's going to n minus 2, n minus 3. Okay. So we're going to have to figure out some pattern where we create this function rotate matrix. Wait, was that? Stop. This is what I want to show you. We create a function rotate matrix. First, we're doing our checks, right? If there's no matrix, you're not rotating anything. If your matrix is just, if we don't have, if matrix length is less than or equal to 1. So if there's just, and we know it's n by n, right? So if that would just be a 1 by 1 matrix, return matrix, right? There was 1 by 1, your rotation's done. Otherwise, we're going to get out the number of layers. So number of layers is representing, we're saying, remember, this is hard because it's a 3 by 3, but in a 4 by 4, a 4 by 4 matrix, we're going through, well, okay, there's a bunch of different ways to do this. I guess this is the solution that I've written out. We can do it different ways. But number of layers is saying, okay, hey, we're going to go through, once you've rotated, we're rotating it. Sorry, let me say it again. If it's a 4 by 4 matrix, your number of layers is 2, right? 1, 2. If it's a 3 by 3 matrix, your number of layers that you need to rotate is actually 1 in this case, right? You just need to rotate it once. So it's like the floors, the round down of how many of the matrix size, the n, divided by 2. So here this is a 3 by 3, 3 divided by 2 is 1.5, rounded down is 1. Here it's a 4 by 4. The number of layers is 4 divided by 2, 2. Okay, so this is just a thing about matrices. Your number of layers in a matrix is your width divided by 2. Okay, and you'll see that with a matrix of any size, it's the width divided by 2 is the number of layers you have till you get to the center. Okay? So if I had a 2 by 2 matrix, how many layers does that one have?
None.
Not none. That would be an empty matrix.
Oh, wait. 2 by 2, so it'd just be 4 squares.
Mm-hmm.
So layers inside of those 4 squares is nothing, right? Or
Nope, it's 1 layer. This is your, this is 1 layer here.
my bad.
Yeah, no, it's fine.
We're looking for like middles, like, but I guess that also counts.
No, a layer is just like how many times can you go around rows and columns. So here's 1 layer. Here's 2 layers. Okay, 1 layer of data elements, 2 layers. 1 layer and then you don't really have it. I guess it depends how you define it. You could say this is a second layer, but you're not doing anything with it. So it's really, I would say this is one layer. In a 2 by 2 matrix, so if it's just this, then you have one layer. And we got that because it's 2 by 2, right? And I said the number of layers is n divided by 2. Right,
So
that's a
it's
trick. So you can draw it out and say, okay, how many layers, basically it's like an onion, right? Like how many layers before I get to the center of the matrix? That's
So
what we're asking. Mhm.
2 by 2 and 3 by 3 just have like one or no layer.
Not
so-
no layers.
I have just like, como si the inner layer is just one. The I can't use the right language, but
So think about it like an onion, okay? We are peeling off the layers until we get to the center, right? So here, how many layers till we get to the center? This is the center. There's one layer surrounding the center. In a 4 by 4 matrix, here's the center. There's 1, 2 layers. Okay? If we had a 2 by 2 matrix, so we're just looking at this here. Okay, if our matrix is just this big, here's the center of the matrix. How many layers does it have to get to the center?
one.
Exactly. 1. Okay, so that's what we say when we're saying how many layers are there? We're saying, okay, how many layers find the center of the matrix, how many layers to get to the center? Okay. So in a matrix, the number of layers to get to the center is going to be the width divided by 2. In a square matrix.
If it's 3, then it's 1.
If it's 3, then it's 1. Exactly. If you have 3, if it's 3 by 3 like this, here's the center of the matrix. It's 1 layer to get to the center. For a 6 by 6 matrix, how many layers are there?
3.
3, exactly. It's width divided by 3. So the reason why you can think about it is, okay, I'm getting to the center, right? So you're just going halfway in. To get to the center of the matrix, you're going halfway and stopping. Right? You're going halfway and stopping. Here, you're going halfway and stopping. So that's why it's divided by 2. Just because to get to the center of something, of an n by n matrix, you're going n over 2 and stopping. So that's telling you how many layers you had to go through to get to the center. Okay? So you always have, unless your matrix is empty, you have at least 1 layer to get there. Okay, questions on this? Okay, so that's our number of layers. Okay, so here we go. This is just, I'm calculating this early just to help us with our loop. So now we're going to say, okay, for each layer, for the width of that layer, oh, interesting. I forgot I did it this way. So, okay, basically here, we're doing it slightly differently. For each layer, for the width of that layer, so here we go. Here's a layer, and the width is 4. Here's a layer, right? The width of this layer is 4. Here's a layer. What's the width of this one? What's the width of this layer? This
Two?
one was 4, exactly, this one's 2.
Didn't
Nice.
realize I was muted, but I was like answering and not getting a response.
Yeah, so here we go. This layer is a width of 4. This layer is a width of 2. So now here, what we're doing is we're saying this one's slightly different. We're going to say, okay, for each layer, take it and move it to the right place. For each layer, take it and now move this one here and this here and this here. So this one is, instead of going row by row, which we can do, instead it's saying, hey, go layer by layer. We're going to go this layer and rotate it, this layer and rotate it. Okay. So, which, if we think about, we'll be able to use recursion if we want. Because you're just going, right? You're solving the same problem, right? This is a really good example of recursion. You're solving the same problem over and over again. You're taking a layer and rotating it. And you keep doing that until your base case, which is the layer is of size 0 or 1. Okay. Okay, so for each layer, for the width of that layer, rotate all the elements of that corresponding index. Okay, we only have 15 minutes, so I'm hesitant to start us on a replit. I am, let me see, I don't want to show you the solution either, but let me see what could be helpful. Okay. I think I'm going to assign a homework to get us a little bit more prepared for the meat of this function. And we are going to, next class, next week, which is going to be our last week doing matrices, we are going to focus on how to rotate this matrix in either this way or potentially another more creative solution. But we are going to look at the indices, and see, okay, when we calculate it, what does this have to switch to? And as we go layer by layer, how are we switching these indices around? So it's going to be a bunch more bring pen and paper. But next class, we'll finish rotating the matrix. And then we won't look at matrices again because I don't like them. But no, not just because of that, but this is like they don't come up that often unless maybe you're working at an image company or something and they're going to ask you about rotating images. And that's the same thing as this, right? They're going to say, okay, we want you to rotate a matrix. They might ask you some other things too with images, and that's going to mean working with matrices. But if it comes up, it's probably going to come up the zeroify or the rotate matrix. So anyway, next class, we're going to finish on rotating matrix. And we will do a replit where we're going to go over pseudocode and then try to code that together. Any questions on matrices? I know this was a coding light class. I apologize for that. Next class, you'll get your hands dirty. Any questions on matrices and on this problem?
We want to use like a swap function, right?
So yeah, you're going to have to say, okay, I'm switching these 4 elements around, right?
Yeah.
You're going to say this goes here, this one goes here, this one goes here, this goes here. But you need to make sure that you can't just say A gets B, B gets C, C gets D, D gets A, right? Because you're going to end up overwriting one of them. So you're just going to we'll go over it, but we're going to have to remember, hey, there's a temp variable to hold the value of this. So that instead of overwriting it, the last one, I can just assign this temp variable. That might be part of the homework, to given 4 variables, swap A with B, B with C, C with D, D with A.
I never did that with the helper function, but it's good to know that you should do that. Yeah.
Yeah. Yeah. So again, there's different ways to solve this problem, right? We were talking before about, hey, people notice that if you do the transpose, which is going over the diagonal, and then switching the columns, flipping the columns, it ends up rotating it. Super legit, great solution. You can totally do that. It's a little less counterintuitive for me, but if that works for you, then come prepared to do that next class. And we talked a little bit about what that ghost function looks like. Otherwise, we're going to go kind of layer by layer, rotating this. So definitely start, I think homework's going to be both swapping 4 or 5 elements and making sure you're not overwriting them. And the other thing is going to be thinking about like drawing out a matrix and drawing out a 4x4 matrix and seeing as you go layer by layer, how are they moving and what patterns are you noticing? So like, do row and column just switch? Or do row and column switch, but column gets something subtracted from it? We know actually that column will get something subtracted because it was last -1, -2, -3, right? Until we got to 0. So anyway, homework's gonna be to kind of think about that. And then we're gonna go over it next class and do replets. So, and there will be office hours and stuff as well. Okay, y'all.
Thank you.
2 hours, crushing it.
Thank you.
Yeah.
Thank you.
All right. See y'all next week. Actually, I'll see pretty much all of you today and tomorrow.
Yeah.
Yeah. All right. Okay. Chat soon. Bye.